Hello and welcome to an introduction to complex numbers. Today we're going to be talking about what are complex numbers, where do they come from. I'm going to cover how do you do basic arithmetic with complex numbers, and we're going to be looking at the complex plane. So first of all, where do complex numbers come from? What are they? Well, complex numbers kind of arise when you have an equation like this: x squared plus 1 equals 0. And if you look at this graphically, you kind of have, so this is the y-axis and this is the x-axis, and you have kind of a parabola like that, and then it goes back up again before it can actually cross the x-axis, which is what it's asking, right? It's asking for which x does this parabola x squared plus 1 cross the x-axis, but it looks like it doesn't cross it anywhere. Now we can try to solve this. Obviously I can take the 1 to the other side, gives me x squared equals -1. But this also doesn't really get us anywhere, because there is no number that if you square it you get a negative number. Because if you have like -3 and you square it, you'll get -3 times -3, which will always be positive, because the two negatives will always cancel each other out. So to get around this problem, mathematicians kind of invented a new number, if you will. It's called I, for imaginary, and it has the property that if you square it you get -1. And you don't need to worry about the details here, the specifics of how that works. It's just an assumption, right? So this is the definition of I. It's if you square it you get -1. So alright, so well, and these numbers you can then you can get complex numbers, or what they call complex numbers. Usually they're denoted with a z. So a complex number would, for example, be 3 plus 2 times I. So you have a real part and you have an imaginary part. So you could say that the real part, like that, is 3, and the imaginary part is 2. You can leave out the I because that's already kind of captured in the imaginary part. Alright, so we have these new types of numbers that can be solutions to equations like this. So for example, let's do another equation like x squared plus, let's say, 2x plus 5, for example. We can try to solve this. So let's actually try to solve this using the quadratic formula. So we'll calculate that. It's going to be 4 minus 20, which is going to give us -16. And usually this means that there is no solution, right? So let's put that in there. Plus or minus -2 divided by 2. But actually, what we can say is that this square root of -16, we can say that this is just the square root of 16 times the square root of -1. And we know kind of the square root of -1, if you take the square root on both sides, then you get that I is the square root of -1. So we can say that this is actually square root of 16 times I, which means it's 4 times I. So the solutions to this equation, which appear to have no solutions in the real number line, actually have two solutions in the complex plane, or the complex numbers, if you will. So dividing out this 2 here, that gives -1 minus 2i, or -1 plus 2i. So those are two solutions to the equation, right? And they are complex numbers. So a solution to this kind of equation, a polynomial or something, can be a complex number if it doesn't have a real number solution. So now we have these numbers, and they appear to be somewhat useful, but I mean, so let's see what we can do with them, right? So let's test them out. Alright, so first of all, we'll try to do some basic arithmetic with them. So we'll try to, for example, add two complex numbers. So we have C1, that's going to be 2 plus I, and then C2, that's going to be 3 plus 2i. And we want to calculate C3, which is just C1 plus C2. So let's just fill it in. So let's do 2 plus I, and then we'll do 3 plus 2i like that. And now it's actually useful to draw an analogy to when, for example, you're working like this, 2 plus x plus 3 plus 2x, that you can kind of group like terms. Like, so this 2 and this 3, they don't have an x in it, so you can just add them together to give you 5, and these both have just one x in them, and so you can add them together. 1 plus 2, it gives me 3x, like that. And we can do exactly the same thing, but instead of x, we're using I with this, so this will give us 5 plus 3i, like that. You could also say that you're just adding the real and the imaginary parts together, right? Because this real part is 2 and this real part is 3, that gives me 5. This real part of this imaginary part, that's 1. This imaginary part is 2. 1 plus 2 gives me 3. That's another way to think about it. Alright, and subtraction, that will be quite similar. So let's subtract, for example, we have 3 plus 2i, and then we have 1 plus I, and we want to get a z3, a new number, that's just c1 minus z2. So let's fill that in. So c1, that's going to be 3 plus 2i, and then c2, that's going to be 1 plus I. We have to do a parentheses because we have to distribute the minus sign. So I'll copy this and then distribute the minus sign. It gives me -1, -i. And now I can just add together the real and the imaginary parts again. So 3 minus 1 gives me 2. 2i minus I gives me just I. So that's subtraction. Relatively straightforward, I think. Because now we'll do multiplication. That will be a little bit more complicated, but still we'll be pretty fine. We'll be fine. Alright, so we have, again, I'll just define two complex numbers. 3 plus 4i, and another one 2 minus I, like so. And we want to find their product, like so. Alright, so let's fill them in. So we have to use parentheses, obviously, like this, and then 2 minus I. And now we can use just, we can kind of distribute this out, right, by FOIL, so FOIL. So first of all, the first terms, that's 3 times 2, that gives me 6. And the outer terms give me 3 times -i, that's -3i. Then the inner terms, 4i times 2 gives me 8i. And then the last terms give me 4i times -i, gives me -4i squared. And now there's the thing to notice, because here we have an I squared, and we know by definition that I squared is equal to -1. So we can just substitute in -1. So that'll give me 3i plus 8i minus 4 times -1. And so now it's just an exercise in adding real and imaginary parts together, right? This will become just plus 5, so 6 plus 5, that's 11. -3 plus 8i, that's gonna be 5i, like that. So multiplying two complex numbers together gives just another complex number. Alright, so lastly we'll do division. So we'll do division of 2 plus I, and then another one, 1 minus I, keep it simple. Alright, and we want to find their quotients, right? C1 divided by C2. Alright, C1, that's going to be 2 plus I, divided out by 1 minus I. And so now I'm actually going to do a little bit of a trick. It may seem to come out of nowhere, but it will help us. So I'm going to actually multiply both sides, the upper and the lower, by 1 plus I. So 1 plus I, 1 plus I. Or I can do this without changing the expression, because if I divide something by itself, then it will just become 1. So I'm effectively multiplying by 1. Alright, but this, how did I get this number? I just flipped the sign in front of the I, right? So this was minus I and I made it plus I. If it was negative 2I, I would have made it plus 2I. If it was 1 plus 3I, it would have become 1 minus 3I, something like that. So you flip the sign in front of the I. So let's work out what this becomes. So that's going to be 2 plus I times 1 plus I, and then in the bottom we'll get 1 minus I times 1 plus I. And down here we're going to use a very specific property that if I have A minus B times A plus B and you distribute this out, you'll eventually get A squared minus B squared. And so we can actually just use this property because we have 1 minus I, 1 plus I, that's A minus B, A plus B. And well, let's just fill this in, right? So we have A that's equal to 1, so we'll get 1 squared minus I squared, like that. And up here, I'll just copy this up here. Alright, so I'm working this out in the denominator. We'll get 1, and then we have I squared, which is just negative 1, so that would be negative 1, which is plus 1, like that. Alright, and then up here, this is just an exercise in multiplication, which we've already done. So this becomes just a half times 2 plus I times 1 plus I. And this will, again, be just some complex number. So we've divided, we've added, we've subtracted, we've multiplied. So all the basic arithmetic works fine with complex numbers. But now, what are they? Well, now we've done quite a lot of algebra, and I think it's good to do something a bit more visual. So we're going to talk about the complex plane. So the complex plane. Alright, so the complex plane, if you imagine just the number line, right? So you have 0 here, you have 1 here, 2 here the other way, negative 1, negative 2, like that. That's all fine, but now the question is, where does I go on the number line? Well, it's not really some number because it's kind of defined to be something completely different, right? Well, mathematicians have decided that I should actually go on a line perpendicular to the real number line right there. So you'd have I there, and then just one more unit away you'd have 2I, and then down here you'd have negative I, negative 2I. Alright, so this is a bit of, this kind of comes out of nowhere, but I'll justify it in a moment. But first of all, so now, first of all, let's see where the new complex numbers end up in this complex plane. So say I have 2 plus I for my complex number. Let's see where that becomes. Well, we'll first of all look at the real part. That's going to be 2. And then we look at the complex part. That's just I. So we'll put it up in I. And then our number actually goes right there. So that's where our number goes. So let's do another one. 3 minus 2I. So 3 minus 2I, well, the real part, that's 3. And then minus 2I, that's there. So our number should actually go kind of right there. Like that. So that's the way complex numbers kind of fit into this, in this complex plane, if you will. And I will do one more thing in the complex plane before I call it quits. And that is multiplying by I, because that kind of has a nice intuition. Multiplying by I. Alright, so multiply by I. So I will just draw another complex plane here. Like that. This is 1, 2, 3. Negative 1, negative 2, negative 3. Negative I. Negative 2I. Negative 3I. And then I, 2I. 3I, like that. Alright, so what we'll do, well, first of all, we'll draw a complex number, let's say z, let's call it 3 plus I, and that kind of sits right there. And so now, what I'm going to do is I'm going to create a new complex number w, that's defined as z, but multiplied by I. So let's work out what that becomes. So it's going to be I times 3 plus I. it's going to be 3i, and then I have I squared, but that's just negative 1, so that becomes 3i minus 1, or rearranged a bit, negative 1 plus 3i. Alright, so let's draw w, so this is c, let's draw w, that's negative 1 times 3i, that's right there. Alright, so if I draw now a line to the origin like that, and I draw a line to the origin like that, these two lines are always perpendicular, so they always make a right angle. So effectively what it means if you multiply by I is you rotate by 90 degrees, multiplying by I. So I'll do another example really quickly. If I multiply W by I, for example get V. So V will be I times negative 1 plus 3I. I'll move down a little bit, and I'll get negative I minus 3, just minus 3. So negative 3 minus I, like that. And if I draw that one, that will be negative 3 minus I, that's going to be right there. And indeed, this one's also perpendicular to W, because we've rotated 90 degrees, like that. So multiplying by I gives me a 90-degree rotation, and that's also why mathematicians decided to put I kind of perpendicular to the real number line. Because if you multiply 1 by I, you rotate by 90 degrees, and you get 2i, and if you multiply by I again, you get I squared, you end up at negative 1, so you've rotated 90 degrees twice, or just 180. So that's that's multiplying by I in the context of the complex plane. Alright, well, thank you for watching, and I'll see you next time. Bye bye.